Hi, this is MAT221, Calculus 1. This is Mrs. Johnson. We were in the middle of this example in section 5.3. We used the calculator to evaluate the change in the population from 1 to 2 and got 1.44 million in bacteria. And then we knew that the population at time 0 was equal to 5 million. So if we look at this equation up here, if we know that this is 1.44 million and we know this is 5 million, then f of 1 will equal the solution to this equation. So f of 1 will be 6.44 million bacteria, which is the answer to our problem here. It says estimate the total increase of the population during the first hour and the population at time equals 1. So the increase in the population during the first hour was 1.44 million bacteria, and the population at time equals 1 is equal to 6.44 million. Oops, I'm sorry. So going back and just reminding ourselves the difference between an indefinite integral and a definite integral. You should distinguish carefully between a definite and indefinite integral. The definite integral, remember, has the bounds, and the answer is a number. The answer is the accumulated amount of change of the antiderivative over the given interval. The indefinite integral has no bounds, and remember, is the family of functions that is the antiderivative of the function. So the connection between the two of them is by the evaluation theorem, which is sometimes called the first part of the fundamental theorem of calculus, which says that if f is continuous, that the definite integral is equal to the indefinite integral evaluated, or I should say the antiderivative function evaluated at the upper and lower bounds. Sorry, my clicker is quite sensitive this morning. So in this particular slide, it's just going back to remind you of those formulas that we have from section 4.8, which you have a worksheet that has all of these in there also, reminding you how to take antiderivatives of the basic functions that we learned from our section 4.8 having to do with antiderivatives. Remember, we don't take the more difficult antiderivatives like going backwards from the chain rule or going backwards from the product rule or going backwards from the quotient rule or other functions that are more difficult. Those actually will happen in Calc 2. In Calc 2, we will find all different other types of techniques of integration called integration by parts, integration by U substitution, integration by partial fractions, integration by trig substitution, and so forth. But right now in Calc 1, we only have to take the antiderivative of these basic functions, going basically backwards from what we know about derivative functions. So I'm going to look at a couple of applications here and then look at the last topic, which is on the average value of a function. So remember, both displacement and distance traveled can be interpreted in terms of areas under a velocity curve. Remember, displacement is simply the integral. So the integral will always give us, of a velocity curve, will always give us the displacement. So an integral is giving us the accumulated amount of change in the antiderivative over the given interval. In this case, from t1 to t2. In this case, it would be whatever this area is, which would be a positive area, whatever this area is, which would be a negative area, because the derivative curve is lying below the x-axis, and here would be a positive area. So what this would tell me is that the particle or the object moved a1 amount, and it moved in the positive direction from t1 until this point, and that it reached a maximum value, a local max. Again, this is a local max because we're looking at a derivative curve, and this is a derivative is positive, then 0, then negative, therefore locating a local max of the antiderivative. Then the derivative is below the x-axis, so the particle or the object moves downward. How much? This amount. From this point to this point until it reaches a local minimum. I know this is a local minimum because this is a derivative curve. The derivative is equal to 0 there and changes from negative to 0 to positive, therefore a local minimum. Then the object moves in the positive direction. How much? This much, A3. And then reaches another local max at its endpoint. So the displacement, or in other words, where it ends up from where it began, is given by the definite integral. The distance it traveled, however, is it traveled A1 plus A2 plus A3. In other words, it traveled this amount plus this amount plus this amount. And we take this as a positive value, the part that is below the x-axis. So what we do is we take the absolute value of the curve, which I did on the calculator earlier. We take the absolute value of the curve, and then we can find the total distance that the object actually traveled, not its displacement. Remember, displacement gives us the difference from where it started to where it ended. This tells me how much did it actually travel, its total distance. So let me give you an example of how to do this. A particle moves along a line so that its velocity at any given time is given by this velocity curve, measured in meters per second. First, they asked me to find the displacement of the particle during this time, then find the distance traveled over this period. Okay, so finding the displacement is always easy. We simply find the integral. So the integral is going to be, the displacement is going to be s at 4 minus s at 1, which is the difference between the position curve at 4 and 1, which is simply the integral from the definite integral from 1 to 4 of the velocity curve. Now we can do this pretty nicely now using the fundamental theorem of calculus. So we say, okay, the antiderivative here is taking the antiderivative 1/3 t to the third, 1/2 t squared, and then 6t, subtracting. And then again, I'm using this notation. I'm evaluating this from upper bound of 4 to a lower bound of 1. In doing that, I get -9/2. Now, I didn't show all that work there, but you can definitely see how I did that. I put in 4, so I get 4 to the third, 4 squared, and so forth. And then I subtracted the two values to get -9/2. This means that the particle's position at time 4 is 4.5 meters to the left, or to the negative side of where it started. Part B, though, asks us for the total distance it traveled here. So in this case, whenever the velocity is negative, we want to make sure that we are taking the absolute value of that, or taking that into account. On this particular function, if you note that if I factor this, right, you can factor the velocity to see where the zeros are. So from on the interval from 1 to 3, the velocity is negative, and then the velocity is positive from 3 to 4. So what I do is I break this up and I say, well, I could either take the absolute value of the velocity curve or break it up into two separate intervals. Now, one thing nice here, I would have to, if I had this option, I could do it on the calculator. In order to do it by hand, I would have to break it up into the intervals. Where the interval is, where the velocity is negative, I'd have to break it up into those intervals. And then where the velocity is positive, just keep it as positive. So doing it by hand here, I broke it into the two pieces, found the antiderivative, and evaluated. Again, I'm not showing all this work here. This is a lot of arithmetic here that I'm not showing. But evaluating here, I'd get 61.6. Notice I get a positive number here, which I should get, because I just want to know how far the object actually traveled over this interval. I'm going to stop the video here and actually show you some of this on the calculator. All right, so let's look at the calculator with this problem too. So what I did here, we don't have a t here, so I just used x. My function was t squared minus t minus 6. I left this here, by the way, from our last examples, because we're going to use that absolute value here. But for right now, I turned this equation off. So let's just graph the velocity function. So here's the velocity function that we're talking about. Now, of course, we're only looking at the velocity function here from 0 to 4. And you can see that, or actually was it from 1 to 4? So yeah, we're only looking at this velocity curve. We only really want to look from 1 to 4. So I'm going to actually set my window. So I'm going to just look from 0 to 5. So I'm a little bit, sorry about this. The sensitivity of this calculator with my clicker is pretty sensitive. So I have to. So this would be my velocity curve that we're looking at. Now you can see, definitely you can see if you graphed it on the calculator, you can see the velocity is negative from 1 to 3 here is definitely negative. And then positive from 3 to 4. So there's two ways we could do it. We could break up this interval. So break it up in from 1 to 3 and then make this, whatever this value is, make it positive. And then break it up here from here. So I could do this. I could say, let's take the integral from 1 to 3, and it'll shade in that region, and it gives me a negative value, which is negative 7 1/3, which makes sense. And then I could do this and say, what's the integral from 3 to 4, and it gives me 2.833. And then if I just add those two values together, I could say, well, actually I would make it a positive. It was negative 7.3333. Sorry, my sensitive clicker here is here we go. So I'm going to put that value, which is the negative of the integral that was below the x-axis, and then I had 2.8. But I want to add these together, Mrs. Johnson. 2.8333. And I got this. Now, if we change this to a fraction, it won't let me change it to a fraction, but if we change that to a fraction, we got, before on our PowerPoint, let's see, we got 61/6. What is 61/6? Let's try that again. 61/6. There we go. That's our number that we got before, right? When we had our other entry. So you can see that we got the same exact value there that we should get, right? So going back to the curve, what are we doing? We're saying that overall the object moved in the negative direction 7.33333 units, but then moved in the positive direction 2.83333 units. So its displacement, right, we found its displacement first, which is different than how far did the object actually move. The object actually moved 10.1666 repeating units, or 61/6 units. The other way we could do this is we could use the absolute value curve here. So I'm going to turn this one back on and turn the original curve off so you can see the graph. So if I took the original curve and just took the absolute value of the velocity and then took the integral let's do this. Took the integral from 1 to 4, the calculator then gives me this answer. Now notice again, it should be 10.166666 repeating. The calculator is smart, but